Bjorn Stevens needs no introductions. I talked this morning about a slow evolution of climate modeling. I think he's going to talk about fast evolution of climate modeling, and then we'll have a very nice discussion.
Yeah, I saw Thomas in Africa. We were at the World Climate Research Program Open Science Conference in Kigali, in Rwanda, and he asked me if I would tell you a story that I told there. So I'm going to relay that story, and it's about how climate change is changing climate modeling. And I added a bit in case who was in Kigali, who saw the presentation in Kigali. What I added here at the end a little bit is what EERIE has to do with it. So the story begins about a climate ago, more than a climate ago, in 1988. And in 1988, the United States had just experienced the second of two rather hot summers. And what I show here is a time series of June temperature anomalies from North America. So red warmer, blue colder, and these two warm Junes. And there was a senator in Colorado at the time. His name was Timothy Wirth. He was a Democratic senator, and he had gotten his PhD at Harvard. So he's Harvard-educated PhD. He ran the Energy and Natural Resource Committee of the Senate. And he was familiar with this kind of obscure idea called global warming. You know, he's a senator from Colorado, after all, where NCAR is located. And he saw in this hot summer a chance to make this obscure theory that he knew about somewhat tangible for the American public. So he organized hearings at the Senate in the midst of that hot summer. And he invited this guy here, James Hansen, to testify. And he asked Hansen why he thought the United States was having such warm summers. And Hansen said it's global warming, and he's sure about it. 99% sure about it. And the global warming is due to human emissions of CO2. And this has profound implications for people and economies. Well, Wirth's idea was pretty successful, and the testimony led to headlines. So global warming was suddenly on the front page of the New York Times. Here, this is Friday, June 24th. Global warming has begun, expert tells the Senate. So if you think about it, 1988, who were the powers that be at that time? In 1988 in the United States, anyone know? Ronald Reagan. Mm-hmm. The UK? Margaret Thatcher. Germany? Helmut Kohl. They didn't like this sort of stuff on the front page. So they did what all good political leaders would do at the time, is that they said, you know, maybe we should refer this to committee. And within a year, less than a year, this 2-page memo was agreed upon between UNEP and the WMO, which led to the formation of the IPCC. The IPCC was formed to do 3 things, 1, 2, 3, and they're written down here in the back. You might not see it, but it was formed to make assessments of scientific information on climate change. The idea was to make assessments of the impacts and to discuss strategies for responding to these things. So the whole point of the IPCC was to make ladders less tangible. It was sort of the anti-Tim Wirth strategy. It was to bureaucratize the discussion of climate change. So where has that gotten us? Well, if you look back, this is the exact same time series, but now instead of showing June, North America, I show every month for the world. And it goes back 100 years further to 1850, but it ends here in 1988. So that's where we were in our story in 1988 when Hansen testified. We had a time series like that, and we had an idea like this. So this is Suki Manabe, his Nobel picture, and his ideas of global warming, which Timothy Wirth was trying to make tangible, and Ronald Reagan was trying to bureaucratize. So we had that, but it didn't take very long until this guy's ideas were used. So Hasselmann in 1979, already before 1988, had come up with ideas about how you would detect whether or not this was due to CO2. And it didn't take very long, 1993, until Gabby Hagel, who was a postdoc in our institute from math, worked with the team. Jinsong von Storck's husband, Hans von Storck, was the group leader at the time. And they used these methods to show that, sure enough, with 95, not 99, Hansen always exaggerates a bit, but with 95% certainty, this was due to CO2. So already by 1993, we had some good scientific justification for that. And if that wasn't enough, we could have just waited. And the signal, by the way, this was 2 big El Nino years, so it wasn't so obvious that was due to global warming. But we didn't have to wait very long until you didn't need to be Gabby Hagel or Hans von Storck or Klaus Hasselmann to realize that this was the fingerprint of global warming and CO2. In the meantime, I mean, we can write a formula for the climate sensitivity, which underpins the growth of this curve based on the CO2. And we can write this formula down, and it just depends on the mass absorption coefficient of carbon dioxide, the mass absorption coefficient of water vapor, the amount of cloudiness, and observations of surface albedo and things like the Planck function. But the point being is that we understand climate sensitivity very well by now. And so we've learned a lot. And we've written it down in report after report after report after report after report. And we've done it for all 3 of the charges that the IPCC gave us. So you can look back and you can say that even though the goal was to bureaucratize the process, the IPCC didn't turn out all bad. In fact, it was a very effective way to build a consensus, a social consensus about these ideas, and how to answer a few abstract questions about the world. Abstract in the sense is the world warming? Are humans responsible? Does it matter? Can we do something about it? I mean, these are the kind of abstract questions that they were answering. In the meantime, shit happened. But most of you are probably thinking about September 11th, 2001. Anybody from South America here? No, you might be thinking about September 11th, 1973. That was the coup in Chile. But I'm talking about 2023. And in September 11th of this year, that happened. And that is Derna in the north of Libya. And on the evening of September 10th, a Mediterranean storm called Daniel came across Derna and dropped between 15 and 25 centimeters of rain in a 24-hour period. Inland, the rain amounts were 45 centimeters. And that led a dam to break. And that led another dam to break. And that led to a deluge here, which killed anywhere from 5,000 to 25,000 people. Almost as bad as the fact that so many people died is that we don't even know how many people died. I find that a real travesty. Now, you might say, when you look at that, this is just social dysfunction, you know, brought on by the history of colonialism and foreign intervention, which maybe destroyed Libya's ability to function properly. But we've seen other things in other countries, not this dramatic. And I have the feeling that even in a situation where as difficult as it is to function in Libya, that had people been able to imagine that, it wouldn't have happened. So I just can't believe that if someone had been able to imagine that, people had written reports about the dams, like IPCC reports, you know, on pieces of paper, filed away, brought to their superiors, and said the dams were in a state of disrepair and dysfunction and needed to be improved. So it was known, but it wasn't tangible. Was my feeling is the what that really meant wasn't understood by the people who could have maybe done something about it. Otherwise, this wouldn't have happened. So the difference is that now climate change is here. It's not a question, is the Earth warming, are humans responsible? But it's really something that is here and people are dealing with. And people are asking all sorts of questions. Are large-scale DERNAs possible? If you look at the IPCC report, it says that sea level rise could be more than 15 meters by 2300. That's absurd. I mean, that's just a crazy, 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 crazy number, right? And to get to 15 meters by 2300, it means it gets to about 6 or 7 meters by the first decade of 2100. That's not so far away. So is that realistic? We don't know. We just speculate about it. How will fires change? How will El Nino change? So we're speculating, will we have permafrost bombs? Will, in the case of this community, is the MOC really going to collapse? So what you see is people speculate because we don't really know. And so this lack of knowledge is also a source of anxiety. On a much more mundane level, what you found, I asked colleagues to collect newspaper clippings. And, these are things mostly from this year. I think, the July 2023 Senegal paper here, Chinese, Japanese down there. So everywhere you look, there's articles coming out about unprecedented changes, and people are asking, the questions they're asking aren't really abstract anymore. They're not asking, is the world warming? They're asking, what's next? What do we have to prepare for? And the answer is we can't, in many cases, really tell them. And even if they don't want to know, and we just saw this referred to in Julie's talk, even if they don't want to know, and they don't want to ask what's next, they're being forced to. So we're seeing a whole range of new financial instruments coming into play, which are forcing companies to actually assess their risks and their contributions. There's other legal things in place which are making people wonder about their liability for risks or damages. And so there's this incredible pressure for information, and that's what that slide that Julie showed with all of these companies, the new economies that are developing to try to meet this need for information. So people are worried, people are asking questions, people are being forced to ask questions, and the reality is that the information we can provide them is rather meager. You can say what's missing. I mean, we had the memo, 2 pages, and out of that memo, we had our reports. We counted over 35 years. We've written about 50 of these, 47. And if you count the number of pages, there's 30,000 of them. And if you weighed it, it would be about 100 kilograms. So we have that. So what's wrong? And I think there's 2 things wrong. I'm going to mostly talk about the second one, but I'll come back to the first one. One is that the quality of information we can provide is not at the level we need. But there's another much more simpler thing that's wrong, which is that what this guy says here is this is an interview in Grist magazine in 2018. It was on the 30th anniversary of the Hansen interview, and they asked him what's the biggest mistake we made. And he said, we never found a way to make the issue tangible to the average person. So we had climate change. The powers that were in the 1980s did a good job of bureaucratizing the process. Everybody felt like they were contributing by writing lots of reports. But what Timothy Wirt did in 1988, and what we failed to do in the intervening time, is to make these changes tangible to people. And when I think about making climate change tangible, I like to use this picture because for me, it says Salvador Dali, and it's in the Reina Sofia in Madrid. And I like it because Dali is a surrealist, and thinking about the future is always a bit surreal, but it kind of symbolizes for me what we're trying to do. We're trying to help people imagine their future. And there's no better way to think about the future than the idea of someone looking out the window. And so how can we make it possible for people to imagine different futures in ways that they can understand? Here I work in pictures, so we can imagine the storms of the future. We can think about how that translates into clouds. These are simulations that we did 6 or 7 years ago over Germany at 200 meters. And I like clouds, so it's a way for me to imagine the future, or the storms, say, of my children or grandchildren. But there's many different ways to make information tangible. You know, for me, it would be pictures of clouds. For a farmer, it might be spreadsheets showing crop losses. For a water manager, it might be raging rivers. But how can we make it that many different people can imagine how the world can be different? You know, by the way, this was 6 or 7 years ago. Now the Japanese have done simulations like this globally, 200 meters. So the world is really moving fast. And here I wanted to make the point that technology has a huge role to play. So a lot of times people like to nitpick and go back and forth, you know, this is technocratic, it's too much technology. But if you think about it, one of the biggest changes in the way we think about ourselves as human was the result of a massive technology project. So you know this picture, right? It's the blue marble. And the blue marble, if people don't remember, it was a photograph taken from astronauts as they were going to the moon. It was the last crewed mission to the moon. And they looked back and they snapped a photo. And this photo was shared with the public. So low-tech photo, very high-tech going to the moon. And it was the first time that anyone saw this thing like that. You know, it's hard to imagine, but people had never seen what the Earth looked like. Imagine never seeing yourself in the mirror or in a reflection pond, but the first time seeing yourself in the mirror. And this was like for the first time seeing ourselves in the mirror. And many people credit this with changing the way we see ourselves. 50 years ago, December 7th, 1972. To mark that, we said, maybe we could simulate that. And so we took our model, which you're using also in EERIE icon, and this is the Southern Hemisphere. This is 1972. The modern satellite era is normally thought about in 1979. So 1972, not much data. So we put the data in the model, and the beauty about physics is that it can tell you things that you don't get to see just by experience. And in this case, if you put it in the model, what we got was this was what the astronauts saw. This is what comes out of the model. But when it's driven by physics, you don't just have to look at the picture, but you can look around the corner to where the astronauts couldn't see and see what the world probably looked like when they couldn't look at it. So here we look at South America. You could put the world in motion so you can see how the cloud fields move in time, which we couldn't capture with a single photograph at that time. But it's coupled, so we can look into the ocean and see the height field. We can see the salinity field and the freshening of the ocean from the rivers. We can see the wind field under the clouds with the temperature field with the upwelling along the Namibian coast, or the wind field here, this very, fine scale structure that extends over the whole planet. We can look at how they interact. And we can zoom in so that you can look out the window, not just in Spain or wherever Dali was imagining the world, but in every place of the world, from Madagascar to Svalbard. So the point is, we have this amazing power now in technology to help people see the world in ways that they couldn't see it before. And maybe we can put that to good use. So we met. A bunch of us, Julie was there, a number of us were there in Berlin, Thomas and Pierluigi and Nikki and others who I might be missing. We met in Berlin to kind of address this question. We said, let's get together and ask ourselves, how can we use technology to help us with this problem? It wasn't, there's lots of different ways to solve problems, but we said, let's ask how we can use technology. So we gathered people from around the world, anybody who wanted to come, and we met for 5 days. We had 2 days of talks, then we had 3 days of breakout sessions, working groups, parallel working groups, all discussing the same questions of saying, how could we use technology? We had people like the head of the IPCC, the head of the WMO, the head of the Senegalese Weather Service. But we also had, I wonder if I can see Jenna somewhere in there. We had graduate students in behavioral psychology mixed in. I should have prepared and find her. So it was quite a mix of people. And we came up with this idea of Earth virtualization engines. And the idea of Earth virtualization engines was an international collaboration to tap our technical capacity so that everyone, and in Tagalog I repeated this and I'll do it here as well, so that everyone knows how climate and climate change affects them and where this knowledge empowers them to act. So this is what we wanted to do. And the idea is we would do it by generating sources of salient information that they could really use, that they could touch, that they could feel, to try to catalyze a change in the broader system of data and services to deliver a just, equitable, and scientifically grounded basis for action. It's a little bit here that's important, is to catalyze a change in the broader ecosystems. So catalyze means that Eve wasn't proposing to do what everyone already does, but the idea was how could we build an infrastructure that would allow all of the logos that we saw in Julie's slide to be that much more effective. Julie was there, right? So Eve's the vision is still developing, and this is still left from Kigali, but we'll discuss later tonight, as what other people think it should do, or how it could change, or things we should consider. It's important to realize those are kind of, I mean, it's so easy to say words like, justice, equitable, fairness. I mean, no one gets criticized for saying that. If I stand up here and I say, oh, we have to be nice to each other, you'll all say, yeah, we have to be nice to each other. I mean, it's really easy. The important thing is that these ideas were really much grounded in the state of technology today. And there were three things that really ground them. One is that we can make simulations like the one I showed. We couldn't do that a while ago. We can bring information down globally to the scale that we, it's kind of funny. A lot of people say, oh, high resolution, it's not everything. We don't need, higher resolution. But if you go from country to country to country to country to country, they all downscale to that scale. They can't go finer because of something I'll say a little bit later. So everybody wants information on that scale, a kilometer scale. We can simulate on a kilometer scale and we can do it globally. So it's just complete nonsense to say that going to a kilometer scale doesn't matter, because everyone in practice does it. And now we can do it globally. Before we couldn't. This is the other magic. I don't know if people have used ChatGPT, but as we were developing these ideas, what really struck us with these sort of generative AI approaches was their ability to assimilate enormous amounts of information in ways that allow you to sort of interact with it, right? So if you use ChatGPT, the thing that's more interesting is how you can interact with, in a sense, the sum of everything that's been written and that it's been trained on, to interrogate kind of what it knows. And you play games and you go back and forth. So it has a way of bringing the internet to life. So imagine if we could simulate different futures with different models, and we could bring that information that is in this to life for people using this AI. So the idea was that this has a way of breaking the data bottleneck that we have when we simulate at this scale. So for us, that was a real change in view. And the other thing is that we've built up this network of people and institutions that know how to do things together, but don't really. We tend to do things in a coordinated way, but there's no real international climate institutions that work together. Close examples would be ECMWF, but even the Brits, the Brits are there, sorry. ECMWF is an example of something that punches above its weight because people come together. But for climate, we really don't have anything, but we know how to do it. So with these three things, we could make climate much more tangible. But to do it, we need an Apollo program. So for an Apollo program, it's not like we just turn this on tomorrow. There's lots of things that the research has to bring to this, not just the society in terms of the money and the governments. If we really want to get there of making climate change tangible so that everyone has the information or the uncertainty that they need to kind of move into the future, we need the rockets. Those are the simulations. And for the rockets, there's lots of things we don't really know how to build. They don't go fast enough. I'll come to that. We don't really know how to steer them. How many do we need? How many scenarios do we need? How do we spin up the ocean? How do we spin up the land? How do we represent the things that we don't resolve at 1 kilometer? How do we deal with the land surface? So there's a lot of stuff that needs to be done to make the rockets as good as possible. We need the landers. So we can take the rockets to where we want to go, but if we can't actually land and bring that information back to people, it's useless. And so this idea of how to build AI to exploit the data, not to replace the models, but to make an efficient way to skim through the data of the models to give you a rough idea of what they say. And we need the mission control. We need to bring people together in a way that allows people to do this. It can't be one place. It needs to, everyone, I mean, if you want people to use information, they need to be engaged in using it, in producing it. So we need to find ways to build institutions that are distributed in ways that can apply the rockets and the landers to really engage with society. So building the capacity to engage civil society in exploring possible futures, the thought was, will reduce vulnerability. And I have this perverse idea that everyone talks about mitigation, and they don't like to talk about adaptation because they think that people might not worry about mitigation. And I think it's the opposite. I think if we engage people in concretely preparing for warming, then they'll see the need to mitigate much more naturally. So if you engage companies and say, this is what it means to protect your assets at 4 degrees, they're like, well, do we really want 4 degrees? Maybe it's better to mitigate. And so I think also by being more active on the adaptation side, we can do a better job on the mitigation side. So a climate ago, we didn't really have the tools to make climate change tangible. So you could say we were diverted by the Reagan, Thatcher, Kohl group. And maybe that diversion wasn't so bad because we developed the communities and the tools that we need. But now we have the ingredients, and by the end of the decade, we could build institutions that could make the future tangible. And I like to use this example of space travel. So when you think about space travel, we wanted to go to space, and now we constantly occupy space. There's satellites there. We use it for all sorts of things. There's institutions behind. So the human spirit has expanded to space through this Apollo program. The way I think about Eve is how do we extend the human spirit into the future? How do we make the future and the past more of a continuum in our mental landscape? How do we get people to think in the future? And so the Apollo program is really the Apollo program of taking rockets so that we continuously populate the fuzzy future. It's not that we'll know it perfectly, but to begin to be able to think in time in ways that we don't now. We'll need this Apollo program. And EERIE, you guys, are one of our rockets. And so here what I did too was I changed the perspective a little bit, because before we were looking out the window with that person to see what the future, but in some ways maybe other people are watching us now and saying, what are we actually doing? So the argument is that they're counting on us and they're counting on you. So where does EERIE fit in? So here's the figure I showed before. That's when I was showing the Apollo ones, and that's just the wind field. So you see the baroclinic storm with strong winds and light winds and coastal jets. And I kind of think of you guys as the stuff that's under that wind field, which looks a bit like that, because in the simulations we have that. And the question is, if we can represent the ocean at this level of detail, how does that matter in this Apollo vision of scheme, the scheme of things? And if you look really closely, I kind of think somehow that spells EERIE in those. Yeah, I think this was the R. I don't know, but EERIE is there in the eddies. So where does EERIE get us? Well, you know this work much better than me, but there's an amazing amount of work right now, which is showing how high resolution in the ocean affects the atmosphere. And I just picked 2 studies here. So this is one where they looked at the effect. What they do is they take a highly resolved sea surface temperature field. And what we learned from Caroline Clayson is probably not high enough resolved, because the effective resolution is fairly low of these SST measurement data sets. But they take a high resolution thing and then they filter it and they take it out and they look at how the storms change. And what you find, this is Asia, North America, North Pacific, and these are the storm tracks. And what you see is, if you look at the difference between filtered SSTs and not filtered SSTs. So smooth SSTs like we have in coarse resolution models and non-smooth SSTs. So here you get, when you get rid of the eddies, what you see is that with the eddies, you shift the storms more poleward in that case. And here's another study which shows that in shifting the storms more poleward, you get a lot more incidence of floodings in atmospheric rivers. The numbers are actually really surprisingly high in this study. This is fairly recent, well, 2021. That's a bit older, if I remember right, 2019. But the ocean eddy field affects the storms of the extratropics. And there's if you look, like I said, you know this better than me, there's a whole bunch on this. This is a fairly recent one that people have been talking about recently. It's the Jaeger paper, and the Jaeger paper in Nature NJP. I always forget how to pronounce that. But what they found for the first time is when they went to a 10-kilometer ocean in that model, is they compared their, this is their decadal prediction large ensemble with 100 members, and this is a high resolution decadal prediction with a 10-member ensemble. And the main thing here is that if you look at the temperature errors, I forget the mean squared something, but these are big here, blue, and here it looks big here you can't tell, but this big blue in the Eastern Pacific, which is an error, is much less here. And what you find is that they get a much better the difference plot is here, and they get a much better representation of the Southern Ocean. And for the first time using this model, they actually then, this paper is not out, but they ran historical simulations. And for the very, very first time, the observations were in sample. So if you look at all of the history of CMEP modeling, we have no, the observations of the Pacific are out of sample. The Pacific is much more La Nina-like, and the models don't capture that. This model is the first one to actually capture it. And the argument is it's being able to get the right heat transport to the Southern Ocean because of the eddies. And that's what your group is doing. So if we want to understand decadal prediction, signal to noise issues, we're seeing results where the high resolution is crucial. And if we want to understand the pattern of temperature change, it looks like this higher resolution is crucial, particularly in the ocean in this case. So let me step back and put EERIE. So we want EERIE because it'll give us better decadal predictions. It'll be make a more useful system. It seems like it will correct major biases that we've been stumped on for a while. So better models. But how does it fit in to the overall landscape of modeling? And here it's worth looking at we'll take a few minutes on this diagram, and I'll try to explain to you why EERIE has a really special role in the model landscape. This is grid spacing on this axis, so 150 kilometers, 25 kilometers, 1 kilometer. So as you refine the resolution, if you go from here to here, then you need, depending on whether you change the vertical resolution, you need 8 or 16 times as much computational power. So if you have a given computer, in this case Fugaku, you can compute a 1 kilometer simulation at a bit less than a year a day. You can use the computer for that. Or you can use the same computer to compute 25 kilometers at here. In principle, you could say, well, we could go up to here to 1,000 years a day, or 1,000 member ensemble at a year a day. So this axis here is the number of ensemble members you could calculate at 1 simulated year per day. Or if you had perfect scaling, how much you could increase the throughput. So you could simulate 100 years a day or 10,000 years a day. That's that axis. Now, if you think about it, when we think of applications, they line up on this axis. So if we want to do decadal prediction, you practically need about 10 years a day, I guess. A year a day, that means, or you want to be able to run many ensembles if you're going to do decadal prediction. So you want throughputs in here. But if you do paleoclimate, you want throughputs here because you want to run the last glacial cycle. So you might want to run 100,000 years. So you need many more throughputs. If you want to do centennial scale predictions, you want to be here. So here, kind of decadal, multi-decadal. If you want to just look at processes on small scales, you can work down here. So this vertical axis, really, you can think of what application are you targeting. This is what you can do with your computer if everything scales perfectly. That's Fugaku, the biggest, most powerful machine in the world. This is our computer at DKRZ, but it's not unlike the computing you have at other major climate centers. So we're kind of back here about 15 years off the forefront of the field, so we can compute on that line. And then you can put all our favorite modeling tools on that diagram. And what you find is that, well, our real favorite one here is high-res MIP, but if this wasn't, Palmod here is at low resolution, CMIP is here. So I put high-res MIP here at about 50 kilometers, and CMIP is 150 kilometers on average, 133 or something like that. And Palmod is a T31 model often. And on Palmod, you get quite a bit of throughput. But if you look at these curves, they don't have the same slope. They kind of go like this. They don't go like that. Do you know why that is? Why is it Palmod up here? Anyone know? Quiz.
Well, maybe it's because you cannot parallelize when you use
Exactly, that's strong scaling. Yeah, so it's the problem with strong scaling is that strong scaling means that you don't get to follow the machine curve. You get to follow, oh, by the way, NECOM is here. It's still on that line. That was the 200-meter simulation I showed before. The strong scaling curves are flatter than the machine curves. So because as you back off in resolution here, you can't distribute the task, as you were saying, to more and more processors. There's a limit. And if you try to distribute more, you just spend all your time communicating. So this strong scaling curve means that you're flatter here. And if you think about it, what this means is that if you have a CMIP application, then you're here. If you have a machine that this is this big, it means you can do probably 1,000 ensemble members on that machine at the same time. So I call this, a well-optimized model. Most of our models are more down here. And this is the utility envelope, because it's hard to think of many applications where you would want such a big computer that allowed you to do 10,000 ensemble members, right? So if you have CMIP, you might imagine it'd be fun to do 1,000, but most of the time, we're pretty happy with 100 ensemble members. Actually, we're pretty happy with 10 as you go down. So here, if we want 10 or 100, we're here. That means any machine that's out there is sort of useless to us. I mean, it's just a waste of interconnect fabric. So the big machines, as the machine gets bigger, they move this way. And the horizon changes that the applications that used to be computing challenges aren't really relevant for these machines. And that explains a little bit why you see in computing, what we found is that most of our applications which used to use the biggest machines don't anymore. If we want to work on the biggest machines, we have to go this way. We could say we don't care about the biggest machines, but it seems like there might be problems that they could help us solve. So for instance, Eve, when we're talking about 1 kilometer, and we'd like to get a few years a day, is kind of out here. It's beyond the biggest machines right now. But that's why we need to lump it. But we'd like to do things out here, optimize better than we do now, get beyond this sort of optimization limit, get machines bigger, and we could be here. But look at this is what you were saying before. This is kind of a big gap that we have to jump. We have things which are helping us get there. So we have a German national project called the Warm World, which is doing a lot to try to change the technologies to get to here. And we have NextGEMS, which is trying to work at about 2.5 kilometers, which is here. And now you kind of see where ERIE fits in, right? So ERIE, there she is, sparkling. ERIE fills this vital gap between here and here. So that seems practical and kind of boring, and it just fills a gap. Who wants to just fill a gap, right? But if you think about it, there's a lot more, because ERIE, when it sits here and you look at its utility envelope, it goes up here. So if we get out to here, we're never going to get 10 years a day, 20 years a day on these models. We just won't get there. So we'll never be able to do centennial scale applications with here. And there's a lot of interesting things that happen on centennial scales. We'll be able to get them here. It'll be really hard to do fairly large ensembles like you want for decadal prediction here, but they'll happen here. So ERIE occupies this space where it's applicable to many very interesting applications to solve very many interesting problems. It bridges the gap between sort of our existing family of models and what we see as the future generation. So I think it fills a vital gap, and it's really future relevant, because that, even as the curves go out here with ERIE, this is the future decadal prediction systems if we build our climate information system right. These are the models that you're developing now which will guide decadal prediction. It'll guide centennial scale projections, and it will inform us about natural variability on our way to having things here that can help people look out their window into the future. It's also kind of nice for prototyping new applications. So this is a 5-kilometer run we did at the Institute, which is phytoplankton, but it shows you kind of where the EERIE is going because it's a step back from the 2-kilometer model. So we can really run many different applications there. And this is just a kind of fun thing. The first runs we had where we had our kind of simple, this Hamburg model of ocean carbon cycling or whatever HAMOC is called. And you could just look at the yearly cycle. This is kind of going through the months. So this is April. And then we'll switch into the spring in terms of May, and then we'll start seeing things bloom in the north as we get into June in the ice retreat. And, you know, the blooms at the pole in July, ITCZ. So we can make beautiful things out the window, but we can also see beautiful things in the ocean. And suddenly when, you know, so EERIE, as it's pushing the 100-year scale, the throughput, it allows you to look at a lot of rich processes on timescales which go much beyond the sort of tens of year scale that we do with the NextGEPS models and what we would do with EVE. The last thing I want to say here in EERIE is this. This is aquaplanet simulations. This is latitude, zonally average precipitation. And we took our model the same model that you saw, the 1-kilometer coupled model, and we ran it through a sweep of resolution, 160, 80, 40, 20, 10, 5, 2.5. And what you see is how the ITCZ changes. It's a single ITCZ, it becomes double, it moves forward. And it seems to sort of converge somewhere in here at resolutions. The 1-kilometer model we couldn't run long enough, but it seems to be converging here at about 1 kilometer. Maybe it would really, you know, converge at 200 meters, but it's stabilizing. You know, when you go here from, you know, 40 to 20, you see big jumps. So this was in the high resmit range, 40 to 20 to 10. Even the storm tracks. You know, I found that really fascinating in this model is that the difference between a 40 and 20-kilometer model in the storm traps were huge. So even the storm tracks, which seem to be a large scale thing, seem quite sensitive to the small scales. I point this out because in our institute, I don't know how you'll do it with the other models. The nice thing when you work at these resolutions here is that you can use convergence as another way to inform yourself about the solution. So normally when we make a climate model, we just run a climate model at some resolution and we tune all the physics and we have machine learning and we tune it more and we tune it more and it works and it says, look, here's a good climate, and we compare it to the mean climatology. If we change resolution, it doesn't make any sense to compare it to the old model because we have to tune it again and tune it again. So we have 2 models at 2 resolutions, but resolution isn't what really connects them. There's all of the parameter choices we make. As we get to simpler models here, it's a lot easier to try to infer the behavior of the system from the trajectory as we change the resolution. And so the EERIE model for us in the Institute is really allowing us to work in this space between 1 and 10 kilometers and looking at how the solutions converge to infer the answer rather than just trying to make the best 10-kilometer model possible. So we argue a lot for Jinsong and Dion because they say, the climate's crappy. And I said, I don't care. What matters isn't how crappy the climate is. What matters is how it changes in going from 10 to 5. And you don't fool yourself by overfitting it to the observations. So there's a little bit of a tension there. And, you know, here it matters a little bit how you put the model together. You want it to make sense asymptotically. As you go to finer resolution, you want it to still make sense without having to change things. So this is how EERIE fits in to the Apollo plan. So it's going to be key for making better simulations. It's going to be the what do you call it? The bulwark or the foundation for multi-centennial projections of the future. It's going to be the lens through which we see climate variability, and it's going to be the basis of decadal prediction systems. So these are all my assertions. Probably you wrote it in the proposal. I don't know, but I think they're fairly straightforward. And from my point of view, working at a couple kilometers, I looked at EERIE to help us understand how to do the spin up when we work at really finer resolutions. And I look for EERIE to also do these things about helping prototype new applications and for understanding the climate through these resolution hierarchies. So to me, EERIE is really a vital project in the ecosystem of what we're doing. And it's kind of, as a research thing, it's a key stage in our rocket system if we really want to get to the moon and open ourselves up to new worlds as we envision with something like EVE. So I'll stop there. Thanks.
Questions?
You spoke about, I guess, in that second from last slide there, about not overtuning models and sort of, I guess, keeping them pure, but yeah, basically just not overtuning them. What do you think about then the role of sub-mesoscale parameterizations in?
I would try to get as rid of many, I would try to live without them as much as you can. Because if you put in a sub-mesoscale parameterization for the 10-kilometer eddies and you want to parameterize, what happens when you go to 1 kilometer? You lose that connectivity with finer scales. So there might be some practical things, but as a research community, our job isn't to build good models, because we overfit them. Our job is to understand how things work. And I don't think you could say, well, building a sub-mesoscale parameterization makes me understand how the sub-mesoscale works. But nobody really cares about a parameterization as an expression of how things work. There's very few. Name one, actually, parameterization. Name one parameterization that we believe is a good description. Now, there's one that people come up with, but name one. Who does it? Come on, the obvious one.
Radiation.
The what?
Radiation.
Yeah, I was thinking of the bulk aerodynamic stuff. Yeah, so radiation might work. And radiation's nice because it's linear. Every wavelength is separate. But most people would say the bulk formulas are an example of a good parameterization. But I go to a mesoscale workshop, and half of the workshop is complaining about the bulk formulas. They're not right. They don't get this. They don't get this. They don't get that. So parameterizations I always see as a band-aid that allow us to kind of get to a reasonable climatology. And then when we change the model, they get in our way. So I would try to stay away from that, or just be very practical. You just need it because you want to study something else, and that helps you get there. But I'm not a big fan of. So in ICON right now, we just use Magarinsky to do it in the ocean too, and it does a better job than the IFS at boundary layer clouds. And the IFS has been working at boundary layer clouds for decades with sophisticated parameterizations.
Since we're on this slide, for 20 kilometers or 40 kilometers and beyond, did you use any parameterization then? Or you just switched it all off?
Same. Yeah. So people would say, we use Magarinsky, and a lot of people, like from the LES world, a lot of people say, well, Magarinsky is justified for LES, it's not justified for large scales. And I'm like, well, it's called Magarinsky because it was first developed for GCMs in the 50s. It was rationalized by Lilly. But the nice thing about this Magarinsky, it's the only naturally scale-aware parameterization from the get-go, as delta x or delta x times delta y times delta z cube root, depending how you formulate it in its coefficient there. And it just gets out of the way as you go to finer resolution.
I have a question to the first part of your presentation about visualization of storms for future, which kind of await the future generations to maybe sensibilize the generations which now live and have responsibility and opportunity to do something. So I'm absolutely a fan of what you have shown and on the stories, but all the visualizations, they're absolutely fantastic. But I wonder if they have the same destiny as those images of cancer on the box of a cigarette, which do not really prevent people from smoking.
Yeah, I think, here, it's a good point. I hadn't thought about it that way, but I think with the way, my thinking is that, when you give a lecture, you kind of lecture and it kind of makes sense. But then when you do the exercises, then you realize you didn't really understand the lecture. There's something deeply human that when you start working with information, it takes on a completely different meaning for you. And so for me, this is less than just showing a picture of a disastrous scenario, but putting information in a form that everybody can work with it. And that's where I kind of like the AI. So if you look at this e-vision, one of the things we imagine is, imagine if you could run a model for 30 years and you could, do a climate projection for 30 years or 50 years. So you have one model, one scenario, 50 years. And then you could run that model again, maybe 5 times. So you have 5 ensemble members of that scenario. But then you have another scenario with 5 ensemble members and maybe a third one with 5 ensemble members. So you now have 15 possible futures, kind of trajectories into the future laid out on a disk somewhere, you know, on a computer disk. And then somebody comes with another model, they do the same thing. So you have another 15 and maybe a third model. So you have 45 future scenarios. So the way we think about it is if you could use AI on top of that data set, because if you ask someone to analyze that data, it's just crazy, right? You know, plot it. And maybe you wanted a scenario that lied in between. So I really see what our field is doing when we provide a service to society, and you see this in weather prediction happening very rapidly, is it's much less about providing the projections, but more about providing the training data so we can make good tools that can interpret what those projections mean for application A, B, C, D, E, F, G. So each one of the logos in Julie's talk might be working with agriculture, and they develop an app which trains on those different scenarios and provides information and interactivity for the agricultural sector or the soybean sector or the oat milk sector, and trying to understand how to manage their resources. And another company comes, you guys start a startup and you say, okay, I want to work with the wind energy company. So you kind of work out an app that actually learns the relevant information from wind energy. Or even better, if you have 1 kilometer reanalysis and you want to predict future fires, putting a fire model in a GCM is just crazy. I mean, we don't really understand how that works, and things on smaller scales than a kilometer are important. But if we had 30 years of reanalysis at a kilometer, and we had fire maps, which are often at about that scale for 30 years, then you could use AI to look between the fire maps and the reanalysis and find relations, and then use that to look into the future with that same relation. I mean, you have to make assumptions, but it's just a different playground, so to speak, for people to combine data, to combine models in ways that make it interactive to use. And it's not for research. I mean, it's not for us. The idea of EVE is this would be, international centers of excellence, which actually provide this playground for people. And the other thing about EVE, since I'm kind of harping on that, is it should be in different places. So if you're from South America, you should have a South American EVE, because you have your own data that you'll want to bring to it. You'll have your own models that you want to contribute to it. And only if it's owned by the people who use it will the people who use it feel connected to the data. So the idea of EVE is to have these sort of regional centers of excellence, which lay out the data and the computing for people to play with their future. So not just look at pictures like we were saying before, like a cancer warning, or this is a terrible storm, or this is what sea level looks like, but get people really practically planning their communities using the data. And the hope is that in doing that, they'll be sensibilized to the future in the same way we were sensibilized to the present from that Apollo picture from space. So I don't know if that made sense. I really used your question to go on a bit of a detour, but the point would be I wouldn't just use it for the picture. The point here was putting it in terms that people are responsive to. Maybe not just emotionally, but also practically, so that people use it. And if people use the information, they begin thinking about the future. The hope, my secret hope, is that it will help our species develop a different consciousness about the present and about themselves in terms of a global community, and maybe the world would be a better place. Other questions, especially complaints. When I went to Kigali, so I was accused of being insensitive because I showed this Libya disaster. They said, well, it was mostly the Europeans and the Americans. They said that was insensitive. And then other people say, well, talking about big expensive models is not a good thing because not everyone has them. So if you have critical thoughts, throw them out. And it'd be fun to discuss them. Me and say, this is just all technocratic bullshit. Let's have it. I know you want lunch, but a dinner, but yeah.
Jean Song wanted to say something, and then
I just want to, you want to have Apollo, that's fine. And I guess some of us here also want to learn something. What's the effect of ETH in that sense? That has different focus at the end.
Yeah.
And also the design and focus of the analysis, that's we're aiming something still different. That's what we can do with ERIE. we cannot do everything. We cannot do Apollo.
Yeah, that's right. You know, so the point is you want to learn things, and that's what we do as researchers. In learning things, there's some questions you can learn which will fit into a bigger scheme of things, right? So if you learn how to spin up an ocean, this really helps a lot of people on this. So some of the things that you learn will be practical, and some of the things that you learn will just satisfy our own curiosity about how things work. But our curiosity is also an interesting thing, because why are we curious about things? And we tend to be curious about things that, you know, you ask yourself, if you have a question, why are you curious about something, about that? And normally it happens because you're exposed to something that seems like you could understand it, but you can't. So the source of curiosity is often empirical. And one of the ideas of Eve is if we get people using data, that will also create more questions, right? It's like a giant filter. So when people use information, this will pose questions like, you know, all these models, they're all 1 kilometer, they're all high resolution, but damn it, they still don't get the Gulf Stream separation. And we need to understand that. And so our charge, the things we choose to understand, often comes out of the practice of use. And one of the things as a community, I think, is we have to find ways for the things we do to move into the sector where they're used. Because on one hand, it feeds back and creates demand for us to understand things. And then who's a PhD student here? You know, you're all postdocs, PhD students, or people are trained in doing this. They also want jobs. You? Yeah, okay, 1, 2, 3, okay, now they're coming. So, you know, we're doing all this stuff that's super valuable for the world, but there's like no place to work. Really, you know, where you can get a permanent job, you know, you can kind of stumble through project to project that's sort of funding all this. But if you think about when people went to space, what they left behind was NASA, ESA, JAXA. So if we go to the future, we should leave behind the European Center for Climate Projections. And people could get jobs which have twice the salary of your PhD and a nice living doing what you've been trained to do. So how to create this service sector, which we don't have really. You know, if you look at it, we do all the service by writing reports and stuff like that. And then we don't spend time doing what you want to do, you know, understanding things, because we're so kind of preoccupied with writing 30,000 page reports.
Yeah, thanks. A great talk, of course. You wanted critical remarks.
Yeah.
So I'm gonna make another metaphor like the previous comment. You're talking about the Apollo program to generate that image that you showed. But the Apollo program wanted to go to the moon. So where's the moon? Right?
But
I mean, what's the problem we're trying to solve? And the problem we're trying to solve is addressing climate change,
Yeah.
not taking a picture of it.
No, the problem we're trying to solve, I think, is how do we solve climate change? And in my mind, the only way we're going to solve climate change, or let's call them Anthropocene problems, because imagine we get rid of CO2. Are we done? You know, is that it? Imagine we found some magic technology that sucks CO2 out of the air. We'd have a really big problem, because we'd first have to debate about how much to suck out, and we'd want to understand the effects. But we have many other problems. Like if you look at most of the local changes that we feel are from local effects, you know. So the good example, it's another Hans von Storch story, is the Elbe, the river that goes into Hamburg. The effect of the floods on the Elbe have much more to do with dredging of the Elbe than it has to do with sea level change. And if you look at place after place after place, the reality is that people influence their world, and we want to understand what we do, how that influences the world going into the future. So we need tools for that. Right now it's for climate change, and we want tools to help us understand how what we do influences the climate. And we're mostly talking about CO2, but I think there's a whole list of other questions where this sort of tools, let's call it toolkits for managing the Anthropocene, will be useful. So I don't see this as you know, if you say, oh, our job is to solve climate change in that way, then I would say, well, probably you should work on carbon capture or something like that, because that would be the only thing I can see that could technologically solve climate change. And then if you say the other way to solve climate change is to change human behavior, then what is clear is we need other instruments than these 100 kilograms of reports that are written down, because that won't get people to change their behavior. So I don't know if I kind of glanced off your question or if I got it, but I think, going to the moon means really building the tools to help us manage the future in the same way that NASA built the tools to help them manage the space, we're both going into. So that's where I see the analogy.
I mean, thanks a lot, Bjorn, again. One of the criticism we got was that you project a sort of a level of certainty that we can generate essentially with such high resolution models, and that biases will prevail, uncertainties will prevail, and that people would make decisions upon those elements that are sort of not right, because even if you go to high resolution, there's still going to be things that we probably do wrong. So how do we deal with that?
I would turn it on. I said, I think the best thing that could happen is people make decisions based on crappy information. And the reason is because that's the only way in which we'll create a dynamic in which the information becomes good. So information doesn't become good because we wait until, a bunch of people in hats come out and say, information is good, here you go. Information in my mind, in my worldview, is good because people use it. And if people are using it and they find that it's not working, then the pressure mounts, and then we go to the research community and we say, damn it, this matters and it needs to be better. And we make it better. I mean, that's how we do it. And weather forecasting is a great example. I think the budgets for weather forecasting only go up when they do bad. If they do good, then they'll go up. And so I think that the key insight in my mind is to how to make information so that people use it. And I give the example of Apple Maps when it first came out. I remember the maps that would be in the newspaper. Apple Maps shows a map going into a building or a road going into a building. They had all these things that were just really wrong. But when people use the maps, they get better. And so the thing we have to avoid is that people don't use it because it's so bad. But as soon as people start using it, for me, it's just hard to imagine that people won't use it. I mean, they use regional climate models now. And we know that the regional climate models, or he knows that the regional climate models are like there's all sorts of problems, but it helps people think through things on scale. So I wouldn't worry too much about it being wrong. Yeah.
Well, may I make?
Yeah, please.
I mean, a lot of decisions are made on large time scale. If you build dikes for the Netherlands, you make a wrong decision. It's not so easy to repair that. So I think a problem with climate change is people using information, making decisions, taking actions, and the time scale when you make those decisions are not like your maps from Google Maps. I'm taking the wrong. Or I would do the same. I think it's a big issue. It's like plans they are made now in politicians how to build a new society based on partly wrong information. And
so it'd be better if
partly wrong information. That's worrying.
It's worrying, and it would be better if it was right, and then we could be sure it was right. But I think for me the key is more the dynamic of how people deal with the information. So here's an example that I like to give is agriculture in Europe. Imagine the scenario that the amount of rain we get is about the same or a little bit more in the future, but it all comes in the winter, or more comes in the winter than in the summer. So the summers dry out. It's kind of the scenario that people had in mind in the past years. But if you're getting enough rain in the winter, you could store it. And then you could use irrigation. And in fact, then maybe with CO2 fertilization, you'd even have better agriculture because it'd be warmer, you'd have just as much water, you stored it over the winter. So you'd have to build water systems to store that information. But what you would like is people who are doing that planning, they would go to Eve and they would play. They say, well, what does it look like? Let's put this scenario in here. They try it with another model and say, well, my goodness, they're all different. It doesn't help. Or they might find things where, they're actually all fairly consistent. And they're going to say, okay, we're going to just believe it. Or they might come and say, well, this is really important to us because it makes a lot of difference. Can you give us other lines of evidence that allow us? So I see the use of the information as a filter for what sort of questions are posed to the knowledge community. I mean, academia. And so for me, it's less important that it's right or wrong. It's more important that it doesn't pretend to be authoritative. You know,
That's okay, I agree
yeah,
with you.
and you need to give people an ability to interact in ways that, you know, they can look at one model or another. You can't have one model to fool them all, or, you know, one, yeah.
Can I challenge Ryan on this
Yeah.
one? Because Wilco gave a really nice example of the Netherlands having built the dams to keep the water from the ocean coming in. But now they've realized that, well, actually, now they also keep the water from going. We had so much rain inland that now the dams are a problem. And so you, with your global studies, showed that we can get some types of storms that come from the Atlantic, which have a different structure and have a different water loading and can actually create that much precipitation. Did we ever see those in regional models?
No,
Ah.
no. Yeah.
Yeah.
No,
So that is a huge risk, isn't it?
Yeah.
So you planned that for decades.
Yeah.
And you didn't have that phenomenon. And then you came with your global model and you show that we are at risk of those things. And now Wilco's saying we are very worried about that. The dams are not the right answer for the water that comes from the land to the ocean. They were built for the other purpose.
No, I agree with that. Of course, this information it's an interactive, and I agree with you, an interactive process. You come with ideas. The Netherlands is completely rethinking how to manage the water. I mean, in the past, it was just getting the water as quickly out of the Netherlands. And now there is this idea with the dry summers and the wet winters, that the whole idea in the Netherlands is think about how to use the water to keep the water more space for rivers during. So, and that is a discussion with the climate scientists about the scenarios, which of course, has a large uncertainty. And I agree with better models and probably will hopefully diminish the space of the bandwidth of possible solutions in the future.
See, I think on that point too is we forget how we got here. And we're spending all our energy in our community writing reports. It's just really silly when you think about it. When I was at Kigali, Valerie, you can look at Maswal Demal. She gave a talk, and you know what she basically said in her talk was, we need to write more reports. We need to write them all the time. You know, but it was this whole reporting culture, and there's so little sense in our community that people can, you know, how do we get people to really, you know, put the information in their hand, use it, and create this sector, and communicate that this needs to be done? Because I think a lot of people think, you know, we just have reports and then we have to make cartoons which show the reports, and we have to make nice picture stories, and then we have to get the newspapers. And I think that's a very intellectual way of thinking about it. And we saw what happened. We see what happens when we communicate just intellectually. And so how to expand the use of this information in really practical ways, to me, is the leap. And for people who hear about ETH, there's many misconceptions. You know, one is that it's about replacing research. One is it's just about, you know, simulating at 1 kilometer. The other is that it's just supposed to be one center. And I hope a little bit that you see that it's none of those. You know, it's really about creating a compute and data infrastructure that allows people to explore their future and engage as many sectors of society in doing that. And it would make everyone, I hope, more effective. And it would cost a little bit of money, but my goodness, you know, what's money? So.
Have it. Song, and then somebody at the back. Yes.
Yes, maybe I just want to challenge you a little bit more to say that you are saying that ETH can produce tangible information.
Yeah.
And I just wonder whether that is really the case. At least you have to make Apollo Power 2 or whatever, because if you have such high resolution, you have more information on smaller spatial scales, but you also produce a lot more internal variability. So the signal to noise actually probably is reduced. So the information, to make it usable, you produce predictions, but that is with lots of internal variability in there because you resolve more things.
You know, my interpretation of the signal to noise paradox is that when you went to higher resolution, you got better. It was favorable for. I mean, you get more signal and less.
Not sure. That's one possibility. I would say probably that's not necessarily
You guys would be
enhanced.
more of an expert on that.
One
But
of our hypotheses in the EERIE.
That's what the Jaeger paper does
And that's
suggest.
what the Jaeger paper said.
that's what
The
I
case.
don't understand it, but that's what the Jaeger paper said.
So you might be right. And then the other thing is, but this, you know, this can work. You know, you can argue about how good it will be. I don't know if this can work. That's hard to get people to work together in institutions internationally. This is to me the leap of faith here. But it's a good leap of faith because if you look at, if say you go to Africa and you build up a little EEB node for Africa and they have the, you know, they develop models and they run them at scale. And you're engaging people to try to extract information out of that data with AI. You know, what you're doing is you're training a workforce in the economies of the future. So the good thing about this one is that even if it doesn't work, we see also in Europe, I mean, all the countries in Europe are all trying to compete on this sector. You know, we're creating programs which are training people to find their way through data. So this is a bit the leap, but it has the positive aspect that it kind of aligns with things that countries want to do anyway, which is to develop digital competency, to train workforces to work with data. And so I see this as kind of a no lose scenario. Yeah, so, yeah, and this would, I think this, even if there is more noise, this is the filter. I mean, if you have 10 million parameters, you should be able to filter everything, and that's what these things have. So.
There was one on the back and then.
So I would like to point out that you completely ignored one of the branches of the society that actually powered the Apollo program and generally space program, which is the military. Maybe we could also think how we can advertise such a great tool such as ETH could be to the military, because they basically have unlimited funding. They could, like, if we could get their back on this topic, we could basically get any sort of money to and actually give them bad data until we get better, because that's what those military programs do.
Yeah. No, you're probably right. That's probably why it'll fail. Because yeah, it's not my favorite organization. Although if you look at a lot of the things that have happened in the past, there's this you know, if you think of why we have the numerical weather prediction, von Neumann went to the US government and said, look, if we, you know, control theory for flows, if we can understand weather, we could starve the Russians. And if we don't try to starve the Russians, they might be able to starve us. So we need the ENIAC program and we need to make weather predictions. So the birth of weather prediction, that's another story, is built on the military. If you look at the United States dominance in computing, it was because of the nuclear test ban treaty, and they had to develop their computing industry to test their warheads. So the sad story of our history is there's so much that happens because we think it relates to national security. But I haven't gone that far yet. So.
Yeah, a great talk, obviously. Very inspiring. I was thinking, could you elaborate a little bit more on the role of mitigation research here? Because I can imagine that, you know, seeing climate risk locally, you know, sparks ideas on climate adaptation. But mitigation is, of course, a more, say, it's a global thing. If I emit CO2 here in the Netherlands, then there is a further loop to direct impacts in the Netherlands. While at the same time, for especially European countries, countries are aware of the problems and that they need to do something, but want to have some tangible, you know, numbers, science-based targets. These kinds of initiatives are then popping up. So could you reflect a little bit on the role of mitigation research in ETH, and also in light of what Ryan was talking about in terms of the uncertainty that's associated with it?
So mostly when we think about mitigation on ETH, there's sort of it's called the soft mitigation, which is how you change people's mental makeup, you know, seeing the Earth for the first time and realizing that we're a whole. So there's that aspect, is if you can change people's consciousness in some way, you might have, you know, be just that little extra feather that pushes society to act. On a very practical level for mitigation, there's decisions mostly about planning infrastructure that will help with mitigation. So alternative energy. So if you can give people a sense of, you know, how, I think wind is like I mean, wind power is sort of like a velocity cube sort of thing. So how it's very sensitive to slight shifts in wind. So how to plan wind resources, how to plan solar resources based on temperature and dust. So that would be on the mitigation side of planning renewables. For policy, because right now I have another diagram which I didn't show. If you think about our community, we only try to interact with policy. You know, and that was this whole setup of the IPCC. So it's like this little closed dance between politics, science, politics, science, politics, science, and we get the politics to change the law and the science, and we drew these, you know, kind of like Excel science with little, you know, trajectories of overshoot and undershoot and do all that. And when I think of EVE, I think of, let's just skip the politics and let's go to the working level. You know, the water, it still will affect politics, but you go to the water managers, you go to the agricultural, you work with the people in logistics, you work with the energy sector. So how to kind of distribute or to break this little politics science loop, and to take what we do and really create tools that everyone will use. Does anyone go, you know, does anyone know Swiss Topo? Does anyone who knows Swiss Topo? Swiss Topo is like this most awesome app if you go hiking in Switzerland. It just tells you where you are all the time. So you can kind of go on a ski tour and Swiss Topo will tell you, you know, within 10 meters of where the trail is and how to go. So how do you, that's something that's in my hands as a user. It's not. And so how do we put information into people's hands? And so maybe if you're a little, you know, the people who do the integrated assessment, maybe they'd be able to train integrated assessment models on this sort of database and come up with better things that more interact with the politics. But I wouldn't sell EVE on the basis of making a better interaction with the politics, because I think, you know, that's what the reports were designed and they do that. So.
Yeah, that's you. Yeah.
So, well, my question is, as we are observing climate change, I see it as like a voluntary, maybe very dangerous experiment, global experiment. I think we can use it to calibrate the model ensembles and the models themselves to observe the change. And because on my experience, the biggest problem to build climate services is the uncertainty. It's like too large, and for some time it looked like it was impossible to reduce it. But right now, as we observe the trends, and the trends become very apparent, distinguishable from the noise, I think that's also an opportunity, and maybe even we should add an extra point there about model evaluation and calibration.
Yeah, so we can, so let me see if I understood what you're saying. You're saying that, you know, we have models that are not good enough, but because we observe climate change, we get more data and we can use these to make the models better, the existing models. Is that what you were, did I understand that right?
Yes, and of course, as we add resolution, we are never going to get close to the microphysics scale, which is quite important.
Yeah, so resolution.
So we need a way of calibrating the.
Yeah. So resolution doesn't solve every problem for sure. That's why I said there's things that we have to do, you know, you know, at microphysics that these are problems we'll have to solve. You could argue why go to this resolution, because why don't we just use the coarse resolutions that we have now? And I think there's really a practical answer to that, because people don't do that now anyway. I mean, if you look at country after country after country, they downscale. And if everyone's downscaling, why don't we just globally downscale? So pretend the model wasn't even, sometimes I say, imagine the model wasn't even any better. It still makes sense, because everyone wants a downscale and everyone wants a downscale. Why don't we just do it together and globally downscale, at least then it's consistent. So I think for the resolution, the thing about the resolution where we get a real advantage is it brings us to a scale where people live and make decisions. So that's why people downscale. The other great advantage of resolution, forget about all the physics and things like that, is that this, what we were talking about before, the observations that we have in many quantities are on local scales. And so our ability to look at how the models do or interact with data, we're working in similar variables. So right now I work in the atmosphere and we talk about a convection scheme. There's nothing we can observe. We have some statistic called the entrainment parameter, but it doesn't have any physical meaning. We can't measure entrainment. The entrainment parameter is measured by how much it affects the position of the ITCZ and the MJO, but it's an effective parameter. So we could kind of tune that, but really what we end up doing, and that's why I said what we end up doing is compensating some other error in the model. And so I think if that game in my career has been frustrating and I've given up. So it could be that people still have hope that something will happen there, but I don't see a good justification for that hope, because even when you take one model, people who do machine learning, they try to replace parameterizations with machine learning, but I've yet to see an example where someone's made a better parameterization and then applied it to another model. So really what you want to do is if you have your parameterization of ocean eddies and it's machine learned and it makes the model wonderful, take that same parameterization, put it in another model and see if it still works. And usually it won't, and it won't work because for the parameterization to work in your existing model, it had to compensate for the errors it was given. And so that's telling you that it's not physical, it's compensating errors. And as you move into the future, you have problems. And you could say, well, that's okay. All information is kind of only half good. And, we have problems with these approaches. But these ones allow you to think more physically about the issues because you bring it to the scale. And the only reason we go to 1 kilometer is because of that diagram. This guy here, we're just not going to get, because of strong scaling, we're not going to get to 100 meters if we want to look at decades. And we're not going to get to 1 kilometer if we want to look at centuries. So it's just a really practical sense based on our ability to distribute data on a computer about what we could do. There's nothing really magic about 1 kilometer, except it's where people work and it's what we can do with foreseeable technology over the next decades. And so, yeah, that's the way I think about it, at least.
Thank you. Thank you for the presentation.
Last questions. Some of the younger people hiding here in the back. Yes.
I think it's great if you can resolve all the things, but how do you want to distribute that amount of data? You're on all this kind of analysis.
Yeah. So there's these.
You like to use the word magic, and I'm a little afraid there's a lot of work behind that magic.
Yeah, but work is good, right? Imagine. Well, the good thing is the more people who work on this, the better, because then people are thinking about climate change, they're engaged, they're doing things. So the idea that you need to have everyone working, it's not like everyone, if you think how most people spend their time working in the global economy, then, I don't think the world would be worse off if more people work on trying to understand what the data means. But I think when I come back to the data, there is this one thing I learned over the last, especially in Berlin, as the head of NVIDIA was there, this guy named Jensen Huang, and he kept talking about AI factories and distributive data centers. And so in the past, what happened when you have a ton of data is you would build a distributive data center. And a distributed data center is where you go and you get the data and you take it back with you and you do things with it. Now, if you want to learn from massive amounts of data, you can't do that because you just can't move data very. And so what people build are what they call AI factories, is where the data, when you have massive amounts, is collected in one place. And you have a lot of compute at the same place, and you allow people then to compute where the data is and create tools that allow you to find approximate representations of that data that then you can give the AI tool to someone. And then you think too, no one complained about energy efficiency, so we could talk about that later. But if people have these tools, then they can kind of look into the future with very low cost tools. And to me, this is also really attractive because if you go into countries or places where the human capacity is underdeveloped, AI is great because the threshold for using AI to go from input to output is much lower than the threshold for doing that physically. So if you have AI factories and you create public space for people to work in, you can engage people doing things and their creativity. So I don't see that as all bad. But you have to think of this AI factory rather than a distributed data center that we're going to be sending around. You're creating a public space where there's data about the future, where people can go to, like all good public spaces, and try to do useful things. And right now we don't have anything like that. So that's kind of a fun aspect. You wanted to ask a question, I think. Nope, okay. So then I am.
Okay, well, was there someone? Yes.
Yeah, she had her hand half up, so then.
Yeah, I did. So I was kind of observing the whole conversation, and also was kind of thinking, like maybe we do have a bit of like hesitation because we're used to this reports and writing papers and publishing, and we're used to communicating to the politics and policy. But as you said, like we're not used to communicating with the other fields as much and science communication. And you put the example of Libya. And as we know, or as the science suggests, extreme cases are becoming more and more common. And we cannot wait for like one centralized sort of action, or wait for the information to reach in a slow way. So many different fields, maybe it's like water management, building dams, all of these different fields do need this information. And I really appreciate this concept that you're bringing up. And so, and also when we were questioning, is this accurate? I was just thinking, maybe I'm wrong. Like we all maybe use weather apps on a day-to-day basis, and it says it's gonna rain now, it's not gonna rain now, or this is temperature. And if we use 5 weather apps like in a row, they're not ever accurate. They themselves have differences, but we find the use in a day-to-day life and we apply that. So this is not something that we need to think about 100 years, and this is kind of now. And we shouldn't be really hesitating so much. And perhaps like what we're used to doing traditionally from the origin of IPCC to now, we really do have to think about more creative ways, or kind of take the opportunity of the new development. So I really appreciate your developments.
So I think we should give her a hand. That was a great way to. Very well. And, if you take one thing away from the talk, is that let's be creative and imaginative and ambitious about what our science has to offer the world as we grapple with these things. And I think we have a lot more to offer than just bad headlines, which is what we mostly offer right now. So, so if it's not this idea, maybe there's another one that somebody else here will come up with, which will catch fire. But we should really try to think outside of this box of 100 kilograms of reports and so on. So thank you.
The spirit.
Okay. This morning, before you arrived, I said, we have quite a few goodies, okay? But I also said, we can't give them away easily. They need to be earned, right? And I think with your presentation, which, I think was really cool and inspiring, as you said, we thought you deserved certainly one. Number one, it's an RV bag, which probably doesn't get you too excited.
I think RV is like the coolest institute. I got to go to Svalbard and I got to wear like RV snowsuits and RV hats. It was pretty awesome. You really, they have really.
So he does appreciate the bag. So here's number one. And then we have here this book. I don't know whether you know it. It's about the design expedition, and it's from our, award-winning photographer Esther Horvath. And I think this will help you to imagine a mosaic. And everyone who doesn't get a book as a goodie, I think what you get will even be a little bit better. You are going to see Esther tomorrow evening in the other building in person, and she will tell the story that's in the book, to all of you before we break for dinner and have drinks. But yeah, thank you very much.
Thank you very much.
Yeah.